Please, may I ask you for your attention? We are going to continue with the second talk of today. We are for 30 minutes? No, for 45 minutes late. Okay, but no worry, you have 1.5 hours, so
I will be fast.
there will be no lunch then, no problem.
Okay.
Please, Alejandro, thank you very much for coming, for accepting our invitation. I'm really looking forward to see your talk about the communication, because communication is very important for multi-robot systems, of course. So thank you again for coming, and please.
So, good morning, everyone. Thank you, Martin, for inviting me. So, I will talk about our experiences when doing communications in search and rescue kind of like scenarios. And I have divided the talk into main parts. In the first part, I will talk about some low-level issues of communications. There is things that I think most of us we have a subconscious understanding, but I will try to show you hard data of why networking is not so rosy as we used to think. And in the second part, time permitting, I will talk a bit about algorithms we have designed on top of our experiences with multi-hop networking. So just a few words of presentation, of introduction. I come from a center in the University of Zaragoza, which is not that well known outside of Spain, which is kind of a toy West Point, because it's the place in Spain where future officers become also engineers. And, well, they are here taking an exam. And I belong to a laboratory which is called Robotics Perception and Real Time. And, of course, I will be presenting mostly work where I am not the first author. I collaborate with a lot of people. I think our current claim to fame is Orb Slam, which was a PhD thesis of our group. And, well, within our group, there are several subgroups, and I belong to the one that does intervention robotics with multi-robot systems mainly in tunnels, and now we are starting with caves. So why the large and challenging in the title of the presentation? Well, I will show you several environments in which we do experimentation. Chiefly we do in a tunnel which is between Spain and France, which is around 8 kilometers, and that has the properties that tunnels have, which they are quite monotonous, they have no lighting, no infrastructure for sure. It's an all abandoned tunnel. Right now it's the escape route for the proper tunnel, so it's like a side tunnel. And here also is a neutrino observatory, so it's kind of uses for science. We have been to other tunnels where there are other challenges for robotics, like the water in the floor and things like that. And recently we are starting to work in caves. This is an old Roman city where there is a quite rich cave complex underground, like 25 meters underground. You have to go down with a vertical shaft. And there are small caves, big caves, galleries. Some of them have floor, some of them have water. So it's quite a rich environment for doing real experimentation, also very hostile. This is a recent flight. We are now taking data sets. Not everything goes well. This was not the fault of the pilot, which was me. That was a bad gyro. We also had some other successful flights. We hope to be able to use this data for future results. I have nothing right now about caves. That's a grossly misstreamed, overloaded drone taking off, as you have seen. But afterwards, we could save the data. Okay, so as you can imagine, doing robotics in those places it has its own problems. And in particular, communications will have special requirements that we are going to see along the talk. The global idea is that we have a multi-robot intervention team, and of course, as Gianni has explained, there will be some high-level supervision or commanding, but the robots on their own should provide the rest of services, and that means a lot of requirements from the network. We want probably real-time capacities for teleoperation or to have video or feeds or audio feeds. We need that the network stays connected at all times, and well, those things that normally networking doesn't give us. Of course, this year was the bomb drop of the DARPA challenge, which is going to solve everything in 2 or 3 years, and we will have to find a new field of research, maybe. We'll see. But the thing is that this topic is very hot at the moment. And, well, I guess all of us as researchers have a quite narrow field of research. And we design models for our problems, we design solutions, and at some point we have to pass the filter of reality by doing real experiments. And when we do this, we obviously will start with simulations, and in simulation we want to focus on our particular problem, and we assume that the rest will work. And in particular for the networking, we do very daring assumptions. So everything is working fine in simulation, we go to do our first experiments, and things turn much uglier. So my purpose in this talk is not only presenting you, I hope, interesting results, but just to scare you a teeny bit so you keep your assumptions on the networking in check, so you keep the needs that you will have in check before you jump to the real experimentation. So we move into the single hop communication part first. I will go from single hop to multi-hop and then to the algorithms. And well, we are all used to working with wireless. I'm going to talk only about consumer wireless because it's what we use. We don't use special devices. And here on paper, things are quite good. We have good range, good bandwidth. But then things are not so rosy when we start using them. We know this. And of course, in a search and rescue situation, we cannot expect to be everybody within the range of an access point. So things have to change. Basically, the robots move around. The qualities of the links between the robots will change due to this mobility and the interaction with the environment. So the first thing that we are going to need and that I will devote some time is about the need to know the link quality, to be able to react to its changes. This quality is, of course, a function of many things, like the transmission power, which, by the way, has maximum legal limits. The kind of antennas we use. A problem is that quite a lot of the literature on telecommunications assumes fixed antennas, not the kind of mobile antennas that we use in mobile robots. So it's not so easy to find studies for communications in robotics. Then the signal will decay, and it will decay in a way which is not the usual assumption in most papers. And finally, it's very hard to obtain homogeneous links, which is also a quite common assumption in multi-robot community communication literature. The first thing that we can use to measure quality is direct measures from the hardware. In this regard, we can use signal-to-noise ratio, the received signal strength indicator, which, by the way, has no physical unit. Each provider has its magic formula, normally using the signal-to-noise ratio, to give a number which is in an arbitrary scale. The good thing about this information is that it's updated with every transmission, so we can get very fresh data from the network. Problem is that it's measured only during the synchronization preamble, so it may be not totally representative of the real signal that we are getting. There is a relatively different quality metric that is mandated by the 802.11 standards, not always provided by the hardware, that is measured over the full frame, so it should be, if it's available, it's a better representation of the quality of the signal. Then we have derived or secondary indicators, which are computed over a longer time. For example, the bit error rate, packet delivery ratio, or plain bandwidth available, throughput or output without the overhead. Those indicators sometimes are not easy to obtain from hardware, require modifications to the drivers, and the problem is that since they require a time to be trustable, your reaction to the change in quality will be delayed. So that can result in network interruptions. Well, if we start measuring the signal, well, I must say that mostly the most common indicator is RSSI, so the signal strength that it's received. This is a static link, nobody is moving, and we will see a normal distribution that has already quite a difference in power between its extremes. Also, this translates in that links are not symmetric, not perfectly symmetric, so normally this is also a normal assumption that links are symmetric, so we will have to use the worst case for the link. And well, this is when we are static, robots are not static. So we start moving and the signal will start to decay for several reasons. The main reason is distance, which obeys a logarithmic law, different depending on the environment, the materials, and so on. Then we have diffraction, which is the way in which the waves go around objects. Multipath reflections, which is when the wave behaves like a ray and they can be ray traced. Some materials have different absorption properties, and all of this, there is people working on how to do good signal simulations for robotics. They use some probability distributions that, if you check the literature, these names will become familiar. This is how a real signal may look when we are moving. So this is a robot that is going away from the emitter, from the transmitter, and we can see that the sweet spot is not just beside the transmitter, it's a bit more far away. And we see that the signal is quite noisy. Here we can appreciate several effects, which are, for starters, the distance decay, the logarithmic one. This is straight because this is logarithmic scale. Then when we filter for low pass, we have the effect of the obstacles, the environment, all that it's hard to quantify. And finally, of course, we see these fast fadings, which is what makes the signal so ugly. This is in one dimension. Obviously, if we are moving in 2 dimensions, we will have something that is even more complicated. And when we have not just one robot moving, but several, we go to 4 dimensions or more, which for mere mortals is hard to visualize because we can go up to 3 dimensions, normal people. Then we have the genius mathematicians. So this already opens the door to many optimizations. Here we see an example of a robot that has to visit a series of points of interest while relaying the information it's gathering. So it may be better, depending on the bandwidth you have to use, to go a longer path, but better communication. And you can play with which will expend more energy, your movement or your transmission power. Then if we focus on the packet delivery ratio, if we make a series of plots against the received strength at different rates, we see that the higher the rate, of course, the less performance we get. So it may be better to have lower bandwidth to gain range. Also, we see here that the packet delivery ratio, which basically says if the link can be used reliably, drops very, very fast normally. And once it starts falling below 95%, 98%, it's like a snowball. You start to try to retransmit and everything will go to ashes quickly. So seeing this same information from another point of view, depending on the rate you want to sustain, for a fixed packet delivery ratio which gives good communication, you will need to be closer to the transmitter. Another issue commonly seen is the issue of line of sight. Sometimes it's assumed that it affects somehow. Sometimes it's assumed that it will break communication. It's not so clear-cut. Here we see an experiment in which two robots are going away from the base station. Here we see the qualities between the three nodes. And the lead robot, the one more far away, effectively when he goes around a corner, he lost communication with the base. But the other robot, which is closer behind, sees a more graceful degradation in the signal, so it's not absolute. Here is another similar experiment. Here we were trying to ascertain which is a good strength to guarantee communication, so we sent the robot away along this path to see how far it could arrive without losing communication. Here we were using the 5 gigahertz frequency, and just before going around the corner, there was this sudden increase in quality, who knows why, and then this sharp drop in quality to 0, so no communication instantly. This same experiment done in the 2.4 band shows that the robot can go around the corner with higher degradation of the signal, but not so sudden, and it's able to go much, much further. So in this case, it would be a waste to stop the robot here, because we can reach much more far. More things that will affect the quality is the kind of antenna that you use. Here, we had set the threshold for communications at 50% strength. The robot went away. When the signal drops below the threshold, the robot waits, turns around, and comes back. When the antenna is internal, just because the configuration is different, the body is making interference, the signal drops heavily, and you lost communication. When the antenna is external, you see here some effects, but not sure if the going back is making anything bad. Since we are in this course using drones, you can imagine that the antennas of the drones will be positioned in some place. So in 3D space, there will be directions in which there will be more interference. Another problem that has been reported is the height of the antenna over the floor. Small height increases result in a lot more of bandwidth being available. And of course, let's have our antennas higher. But when you have an intervention robot, you don't want sticky things that can get entangled everywhere. So another problem to take into account. Then, since we are doing all of this to have intervention robotic teams, we will need real time. Real time for teleoperation across multiple hops to get feedback on the environment, and common protocols do not support real time. The enemy of real time is indeterminism, and indeterminism is built in these protocols because the random backoff doesn't give determinism. So yeah, just a quick refresher. When we say real time, there are different kinds of real time, of course. Hard real time for anything that can cause the failure of the mission. This is habitual. This is usual in aerospace. You can think also the controller of an airbag. If you miss your deadline, that can be very bad. Then we have firm real time. where you can have some missed deadlines, for example, for video, audio. Things that arrive late are not useful anymore. And then we have the rest that can be of real time, best for communications and so on. It's not easy to obtain these properties with commodity hardware and the usual protocols. That's why in our laboratory we ended designing a real-time protocol, which I will present you later, over wireless. Another enemy of real-time is jitter, which is the deviation from the expected deadlines. And this has been observed to be much higher, even 3 orders of magnitude, in wireless networks over wire networks. As you can see here, the distributions for a single data flow, data stream, when over wire, when over wireless. Finally, lag. Lag is the enemy of control. We know that lag translates directly into a loss of phase and makes things harder to control. This is an old advertisement that you maybe have seen already. Some poor guys are fit with virtual reality glasses that delay everything, and they basically become unable to function. So this will happen in our networks. When we start to accumulate lag, our control will be worse and worse every time. So to conclude this presentation of single link issues, well, even single links can be very problematic. So the first thing that we must assume when we go to multi-hop communications is that every hop in the link will provide his own bad features to the communication. So the problems will accumulate. And now we are going to talk about multi-hop. When we are in a multi-hop situation, basically we are talking about mesh networks in which every node is unequal in the network. We don't have a station, every node has the same capabilities. It may be possible to do without mesh networking. Many consensus algorithms, for example, are proud to say you only need to communicate with your neighbors. So you only broadcast and you hear what is around you, and that's enough for your algorithm. And this is, of course, very good for scalability. But when you have a real team, you will want to have high-level services like video feeds. Maybe you want to open an SSH session to fix something in one robot, and we don't want to replicate all the networking layers to have those capabilities. So it's more common to use some ad hoc protocol that will do the routing for us and will provide just regular connections. There is a standard within the 802.11 set of standards for mesh routing. The problem is that it's not really intended for fast mobile nodes like you can have in a robotic team. There are other protocols that we are going to discuss briefly. So that's the situation. First thing that happens when you are in a multi-hop environment is that in the worst case, you will divide your bandwidth across the number of nodes present because they interfere with each other. And you have to consider that the communication range is not the same as the sensing range. When you want to communicate, you first hear that the medium is clear, and nodes that are much farther away than the communication range can still interfere with you. Then, since the routes will be changing in a mobile topology, it's hard to assume or to predict what will be your bandwidth. So you may have to get by assuming the worst case. All of these problems come in part from the well-known phenomenon of hidden terminal, in which a terminal that is unknown for a transmitter is still causing interference, or also the exposed terminal, in which a node thinks that there will be interference when there will be not. So it's wasting time. All of this will result in degradation of the capabilities of the link. So when we go to routing algorithms, it's my personal belief that most of them are influenced by the sensor network community, which is very strong on this kind of research. And there the necessities are completely different, well, not completely different, but not entirely overlapping with robotics needs. If they want to fill a city with sensors, they want them to be conservative about energy. So they will update the routes quite conservatively. If they observe that a route is broken, then they will try to fix it, for example. Or if they are proactive, they will be proactive at a low frequency. This results in blackout periods, high latency periods, and so on. This was further motivation for the protocol that was designed in our laboratory. Here you have a list of usually mentioned protocols for routing. And here are the two that I'm going to present from our laboratory. Just to drive home the point I was making, simple experiments show these blackout periods I was saying. Here we have a robot which is going around an obstacle, roaming from repeater to repeater. Every time that there is a switch in routes, several protocols have a hard time keeping the communication going, even if they recover it. You can see that the minimum times are in the order of seconds already, and the maximum times can be much higher. And of course, when you are using a multi-robot team, losing communication even for a brief time may mean that you don't hear anymore about that robot. So minimizing that is a must. More examples. Here you can see the performance of the 11S mesh protocol, which is only for one changing link. I mean, we are not talking about many robots changing routes at the same time. We are talking about fixed nodes with only one changing. And coming back to the issue of real time. If you don't have priorities, you will have interrupted streams. And if you have interrupted streams, you have a problem, of course. The usual protocols, TCP, UDP, don't have support for this, of course. And since we are using mostly ROS, we are using this kind of protocols. Now, what happens why that happens when we don't have priorities? Let's assume we have a high frequency topic and a low frequency topic that has much more data to transmit. Well, this is basically a regular, what we call in real time, a priority inversion. The packets enter in the operating system queue. They are split because there is a maximum frame size. And then this series of packets is causing a lot of delay for the high priority topic or high frequency topic. This is in a single computer, but if we go to a multi-computer setup, multi-robot setup, things can get even worse because in the competition to get the medium to transmit, the interleaving of packets may result in even worse delays. So we need to do something about this. When we are in multi-hop situations, this can be even worse because some relays may become critical for the network, they may become overloaded, there will be silent discarding of packets, and we want the high priority packets to be kept over the low priority packets. Also, if there are route switching and we don't have packet ordering, we may receive packets not in the order in which they are intended to be consumed. Also, now going to focus for just a minute in ROS and ROS2. Well, ROS, we know that it was not originally designed for multi-robot systems, just to have several computers, but serving a single robot. And by default, it uses TCP. By default, it uses Nagel's algorithm, that you know that it waits for a bit to consolidate data, so to save on overhead, and this results on also increased jitter. So you can disable this algorithm, of course, then you will get a lot more overhead, because even sending 1 byte will send a full TCP frame. ROS2 is here to fix everything. We know this. And the network layer is a standard, an open standard, and it can be exchanged. And we can do our own implementations, so that's good. But to the best of my knowledge, there is no specific consideration given to wireless communications. So we have to trust the transport layer. And what ROS2 has quality of service. If you have used it, when you create your topics, you can say how you want it to be treated. But the problem is that if you go to the fine print, of course, they will say, this is not a promise to have priorities. You need to have an operating system that supports priorities, hardware that supports priorities, a protocol that supports priorities. So in practice, we have a lot of work to do to get those things for multi-route. And so, because of those limitations, people in our group, chiefly my colleague Danilo Tardioli, designed a protocol for real-time over wireless in multi-hop scenarios with rapidly changing topologies. That is what our multi-robot teams need. So it's intended to support hard real-time, as much as that is possible in a medium that is subject to interference from third parties and so on. It's a protocol that is based on token passing, so it has the problem of self-interference between nodes, and has 3 phases. In the first phase, there is a token that contains all the qualities in the network, so this is a point against scalability. And this token will visit the whole network following an optimized path, a minimum spanning tree, and when it's traversing the network, it will gather all the qualities of all the nodes. And also it will gather the priority of the messages waiting to be transmitted in the whole network. After that, in the second phase, the protocol already knows who is the node wanting to transmit the most priority message. So that node will receive an authorization to transmit, and finally in the third phase, the actual data transfer will happen, multi-hop, of course multi-hop, of the payload. Here you can see a comparison of a 2-hop setup in which on one hand it's done manually by using ROS topics, and on the right is using the RTWMP protocol that can be run with ROS also. And there is a video feed in one direction, and there is a file being copied in the other direction, competing for the bandwidth. Copying a file, maybe we want to update the firmware of our robots on the field, it's always a great idea. But you can see the difference in the quality of the transmission. Another experiment that was done to validate those properties is, again, a robot roaming across 4 stations. In this case, it was compared against a proactive managed protocol. And you can see that only 3 packets were lost in the case of RTWMP. Many more packets were lost in the case of the other protocol. Finally, this comes at a price, of course, because if we have a quadratic matrix in there and we have to traverse a spanning tree before every message, you have a large bandwidth overhead. RTWMP is the one in the left, so in the right. So the more data you send, the worse payload you can have. So who can benefit from this protocol? Basically, the situation I was saying. You need priorities, and you need very fast topology change management, so no interruptions in your communications. If you need this and you don't have too many robots, I'm being told that this can scale up to 32 robots. Then this may be an out-of-the-box solution for commodity hardware. Because RTWMP is so heavy, a lighter protocol was designed by the same guy. And here the priorities are only local. So what it does is basically doing the splitting of messages before passing the messages to the operating system and taking into account the expected periods, so the queued messages respect this period. This was demonstrated by doing control over the network in, again, a two-hop network. Basically, we have a simple underdamped response in which the action, which is just proportional action, and the sensing are going over the network. And the expected result is in black. The only protocol that matches this result is RTWMP. The new protocol POUND, which means priorities over UDP, is a bit different here, minimal difference. And the rest of protocols, well, they are not designed for this, so it's a bit unfair to compare them. But you can see that if you don't take measures to have priorities, you can imagine that your distributed control is not going to work, or your control over the network, or it will degrade very badly. This is an experiment in the tunnel, also again to demonstrate these capabilities. Here you can see the main corridor of the tunnel. Every few hundred meters there are lateral galleries that connect either with shelters or with the main tunnel, the new tunnel. And here the experiment was we have the base station over here, the robotic team will advance, and the lead robot has to reach the shelter where maybe there is people that has taken refuge in case of an accident or something like that. Here there are some wrecked cars, and the lead robot is teleoperated all the time. So the teleoperation is going across the network. Here this is the experiment. I will skip some parts. Everything is being processed at the base station, so the laser scans are received also over the network. The map is being built locally for navigation, but the SLAM is being done in the base station. You can see here the lead robot, which is being teleoperated. Here there is no fancy planning strategy, so basically we knew that a repeater will be good to have over here, so that's what's happening now. The robots are coming to be able to act as repeaters over here. I will go a bit forward. Here the lead robot is entering the gallery, and here you start to see the video feed that is being received in the base station. The video feed is the lowest priority topic, so that's why there are some artifacts. And well, let me move a bit forward again. Here the robot is nearing the cars. This is a tunnel that is used by firefighters to train, so they have set there sometimes artificial smoke. They have even burned some of those cars, so that's why there are like abandoned cars over there, because they use the place for training high. And well, the rest of the mission more or less proceeds similarly. Here the robots are gathered again, and they will start to come back to the entrance of the tunnel. If we look at the data flows that were used in this experiment, we see that there were two high priority, the most priority topics, which were teleoperation and the odometry. Then we had a 200 milliseconds period, we had the laser, and finally we have at 250 the camera video feed. the distribution is more or less around the expected frequencies. So to conclude this part, when we go to multi-hop, and if we expect to do some realistic application, we will need probably, if not real-time, at least firm real-time priorities. And our group has developed those two protocols, one oriented for hard firm real-time, the other one for firm soft real-time. And since almost all of us we are using ROS and ROS2, well, we have to deal with these issues also. Incidentally, there are real-time and safety-critical work groups in ROS2 and ROS2. If you want to be in the loop with these topics, there are some periodic online meetings that you can join. And now I will move to the specific conditions of wireless networks in tunnels. Because tunnels, on the one hand, have specific problems for general robotics, because they are not like an office-like environment or urban environment. They are harder in a general robotic sense. But from the point of view of communications, they have special characteristics that may be even good for us, because the tunnel will act as a waveguide depending on its characteristics, and this will show different signal decay properties. Basically, this happens when the carrier wavelength is smaller than the waveguide, and the reflection, multipath reflection, will accumulate destructively in some places and constructively in some other places. And this makes this kind of effect in the tunnels that produce this effect. This also, of course, happens in pipes and sewer pipes and things like that, when they are big enough. What we have is a near sector where we get the usual signal propagation, but over much larger distances than in open spaces. And when we enter the far sector, we start to see these periodic fadings that have a fixed period and where you can find places with good enough quality and places where communication is not possible. This will depend, of course, on the characteristics of the tunnel. But this will go across even soft direction changes. So as long as you don't have very sharp breaks, the effect continues. This will depend, of course, on the frequency that you are using to transmit. It may not appear at some frequencies or may be too short, but at the regular consumer frequencies, it is observable over long distances. You see there over several kilometers. This is a way of representing this information in a compact way. It's called a wavelet. And the good thing is that it allows to represent where the far sector begins, what will be the frequencies of the fadings. Basically, it's like an ID card of the tunnel. We can imagine that in the future, maybe the places where we expect robots to intervene, pipes or tunnels, may have this ID card computed in advance, so the intervention teams know what they will find inside, for example. Here's an experiment. Okay, those fadings can be observed if you move along the tunnel, but one of the things that my colleagues experimented was on seeing if this can be repeated, if it's persistent in time. They have done this with multiple vehicles. We see here with a drone, and we see here the model that's predicted by the size of the tunnel and the two trajectories with the drone. And we see that they match quite well. So all of the bad things about signals that I said in the first and second part suddenly turn into our favor when we are inside a tunnel, because things can be repeated and there is a persistence, temporal persistence. Here we see the two trips offset with an offset, so you can see that even if they are not perfectly equal, the low effects, the big picture effects are kept. If we remove the logarithmic decay and we remove the noise, the high frequency noise, we see clearly the fadings that are happening in the tunnel. We see how the worst case is getting worse, but the good case is keeping quite well. This immediately opens the door to specific navigation strategies in tunnels. You can use your robots to support each other to go across those bad connectivity portions, and when a robot arrives at a good position, it can summon the rest of the robots, give coverage for them, and then you can repeat this until you run out of robots. And exactly that is what was done in this experiment. I apologize for the quality of the video. It seems the high quality video has been lost forever. Here, the idea is that we are seeing the beginning of the far section, so the transmitting station would be much back, like 1 kilometer back already. And here we see the qualities among the nodes. So the first robot is going, you cannot see it, but there is a threshold of quality here, I think. So here the robot is communicating with the base by using the other two relays. Now it reaches a point where it can communicate again with the base, and the other two robots will come to him, and so this can be repeated until much farther than would be normally possible. We are talking that this is, I think, around 1 kilometer, and as you will see, the robots are able to reach the end of that portion of the tunnel. So the robots continue advancing, continue doing this relay maneuver, so they can reach much further into the tunnel. There is a tunnel category in the DARPA challenge. I don't know if these kinds of things are modeled in the simulation. Somebody knows? Okay, I will have to look into it. And so we can see that finally this robot is permanently stopped to act as a relay with the base station, but the other two can continue even farther forward. What about all of this was done by measuring the signal more or less in the middle of the tunnel, in the cross-section of the tunnel. What happens when we throw spatial diversity into the mix? This also has been measured with different vehicles. Here you see an array of 13 antennas, here only 3. Well, what happens is that depending on your transmitteries and where you measure, you can, for example, find perfectly with the phase displacement, where when one of the fadings is in the low position, the other fading is in the high position. So if you keep the best of the two, then you can have good quality along much larger distances. You can see here 3.5 kilometers. In this example, done with 3 antennas, done over the point where the tunnel has a change in slope, so there is a loss of line of sight. You can go from initial conditions with one antenna where you have points where you will lose communication to a much or quite better status in the whole section. Why that happens is because this is a well-known property of waveguides that can be simulated by ray tracing or by modal theory up to a few modes. And so the simulations give this kind of situation inside the tunnel. Modal theory requires that the tunnel be approximated as a rectangular shape, but it works all the same. And This is the actual conditions measured by that big array of 13 antennas. And depending on where you place the transmitter, in the side or in the center, you will have different fading maps, two-dimensional. And again, this opens the door to specific navigation strategies where instead of going straight, you can chase the good positions in the tunnel. One thing that you can see here is that diversity requires quite a lot of diversity. Some electronics advertise diversity and it's only a few millimeters or a few centimeters. That will not help in this kind of situations. Okay, so that concludes the part about tunnels. And as you have seen, robots are already being deployed in this kind of scenarios. I think mainly now for inspection, especially in sewer pipes and so on. And of course, we as researchers want to have intervention teams on these places. So we can leverage these characteristics to our advantage. And not only for communication, but also for localization. This has also been done. Since this is not the topic of the talk, I have not included it. But especially in sewer pipes, where it's particularly hard to localize in the transversal direction, in the longitudinal direction, these fadings in the signal can give you anchors on your longitudinal movement. Okay, so to conclude the talk, I'm not sure how we are going about time because we started at some strange time. But I will talk now about a couple of algorithms that we designed taking into account the things we have been discussing here. I'm not going to talk of a specific mission. Basically, the normal multi-robot intervention missions, what requires that we can move the robots to specific locations, be it for exploration, to check something, to pick something. That's basically what I'm going to talk about. We are going to give goals to the robots. Of course, depending on which situation you are, you will have different information. But we will gloss over that for now and concentrate on the signal. So the kind of movement strategies that we are interested in, using the taxonomy that Professor Amigoni used the other day, is when you use the real signal, so you don't trust your model, you know the signal will decay, but you don't know exactly how. And we want to keep continuous communication to all of our robots because we don't want to lose any of them. So that would place us here. Incidentally, Antonio, one of those is yours, right? I thought it should be here, but we can talk about this. Okay, we can talk about this afterwards. Yeah, one note about the unit disk model. This is something that if you have read multi-robot communications literature, will have seen. It was quite common, I would say, up until 3-4 years, for sure. And basically, they say, okay, we can communicate in a fixed circle radius. And right now, you should be aware that it's not so simple. I'm not going to say that it is completely wrong because I'm on the record. But I will say that if you want to use this model, you have to be extremely conservative on the range that you are going to use. And even in that case, with the line of sight effects, you may be in for a surprise. So that's why our approach was to just measure the signal and trust what you can sense. As long as the signal decays reasonably softly, smoothly, you can react to it. Well, this is more evidence that when you have real signals, things don't go as models predict. Here there is an application of using relays, fixed wing relays, and going around to keep the relay causes these effects on the quality. So again, models can be wildly wrong, which is what the authors point in the conclusions of their work. So we are talking of an approach which is in this side, bottom-up. The network is king. We will navigate as the network permits, and we will execute our plan as well as we can within the conditions. On the contrary side, we could adopt some model, plan for that model, and then hope that everything goes according to plan. Or at least we need to have a plan B to react. So that's why I call this reactive planning. I will present a solution for open spaces and a solution for cluttered spaces, very briefly. In open spaces, we use this network, but any network that gives you qualities should serve. The networking will tell us which links are critical to maintain communication. Navigation will preserve those links that would cause a split in the network. We used a virtual spring damper system. There are other approaches. And finally, task allocation will try to do its best within those conditions. So for the navigation, as I was saying, we use a spring damper model that is designed to make things stable, that it appears when the signal quality falls below a threshold and starts to exert force to prevent the link breaking. And in particular, we use the minimum spanning tree in the amount of this kind of spring damper systems. Then for the task allocation is when we have to take into account configurations of the robots. If we send robots to 2 simultaneous goals, it might happen that even if we could go to each one with all the robots, we will not reach any of them. This is a deadlock. On the other hand, if we are able to detect those deadlocks, we may have some escape strategy in which we release a robot of its task so it can help the other one. But if we don't take some further measures, we can enter into live locks. That is, there is movement, but there is no progress in the mission. Our solution was pretty simple. It was to send all the robots to the same goal when they are connected by weak links. So we ensure that in the end, worst case configuration will be achieved in which all the robots are contributing to the same task. So we know for sure that the task can be reached or can be discarded as impossible. Because if you don't give explicit order to all the robots, those robots stay here, not contributing to the team. And well, to ensure mission progression, as long as 2 robots become connected, they stay in the same task allocation objective until some task is reached. That way you ensure that there is always progress done through the mission completion. There are several algorithms that can be used to allocate the tasks. I won't stop here because it's a bit not on topic. And here it's a real experiment deploying this solution. It was done with 3 robots that had to visit a few points in the parking lot of our university. Here you see the inverse of the signal quality, that is the force that the springs are making. So this is a spring that it's making the most force to avoid going over the breaking threshold. And as conclusion of this experiment, we again saw wildly differing qualities, not qualities, but ranges among the 3 robots. Here you have one robot that can communicate all the way with the base, and we have a robot that can only stay so far apart of the other robot. The robots are not identical, so that might have to do with it. But I mean, here you can see how having a predictive model cannot give good results. What happens, of course, this won't work as is with complex obstacles. For complex obstacles, if we don't have some master plan, you will reach some bad configurations in which robots get stuck, are impeding the free movement of the team, and so on. So again, here we took the most conservative approach, and we are going to use the robots as relays in a convoy. And we are going to make a plan over this idea. The robots go in and go out using the same path, so you are sure that you are not going to have unexpected situations. And because of this, this can be used not only with wireless robots, with tether robots, or with a robot that can drop and pick relays. So here, our assumptions on the signal are the same, that the signal will decay smoothly so we can react, but that's it. And because of this kind of strategy, only one endpoint will be moving, because either two robots are static or only one of the two is moving. So this is conservative in regard to signal degradation. Also, this can be applied to this strategy of crossing fadings that I just presented you in the tunnel part. Here you can see a simulation of how this would work with real robots. Here the signal model is pretty basic, but that's not the point. As you can imagine, the robots could have very different link qualities as long as they are observing. And of course, this strategy on its own is quite wasteful in a sense. You can think of much clever strategies, but it has safety components that we want. Also, well, this is a view from the control station. Just a curiosity, you can see the quality matrix over there, the information from all the robots. This is going over the network. So it's a simulation, but it's using different computers. And, well, this opens the way to high-level planning in different ways that I, again, won't discuss. But basically, the first task you go to will be the shortest path in terms of distance or signal quality. So you can always be sure that you can reach the task or discard the task. And this means that you will complete the mission. There are ways to add concurrency to this. And here, to conclude my talk, I present you two preliminary experiments we did with this strategy. So you can see again how the signals behave. In this case, we send a team of two robots to the farthest point in the building. And the first robot stopped just shy of the loss of line of sight. Bad luck on our part, because quality reached the threshold we had set. So the second robot went around the corner and went a bit farther. Okay. So we said, let's try again with three robots. What happened in this case? In this case, the first robot stopped even sooner, because it lost the quality even sooner. Second robot went a bit around the corner. And the third robot, well, it went far. Again, this shows that, well, the strategy obviously works. It's pretty conservative. But then again, shows how you need to consider at the bare minimum line of sight effects. You can expect wildly different link qualities and so on. And when the robots are stopped, you can expect also, even then, some strange effects in the signal because of interference. Well, this is a building where there is other people and so on. So all of this can happen. And this is the conclusion of the talk. My final ideas are that the network is critical for multi-robot systems, for most of them. But you don't see it mentioned so often in the literature. Better to get ready beforehand with this knowledge of what will you find in practice. And finally, my personal advice always in this situation: when you read multi-robot, blah, 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 with connectivity constraints, blah, blah, blah. Check if they have real experiments, and if the real experiments are using the real signal, and if they are stressing the signal to see what happens in practice. Because you will see that this is not so easy to find. There is, unfortunately, I must say that the few examples that are very good in general. Because to reach that point in experimentation requires good understanding of the problem and good preparation. Okay, I'm done, so thanks for your attention, and if you have any questions.
Thank you very much, Alejandro, for an interesting talk. Hopefully, we will have a lot of questions. We have still time.
You talk about the problem of the disk model.
The what?
The
Disk
disk
model?
model.
Yes.
And is there any other kind of model that we can use when we imply the connectivity maintenance, for example, of a group of robots?
There are people working on simulating the signals. The work of Mosteo, I think it's pretty on point. I don't know if they have software ready for use. Otherwise, I would advise to use some probabilistic distribution that instead of using the fixed distance gives you a variable quality, and if you can take into account obstacles, that would be even better.
Okay, thank you.
Sorry, could you re-explain or explain a little bit further why, because you mentioned at some point that ROS2 could help with some of the issues you were having, but for understand, but you're not using it yet, right?
Well, my understanding, I have done work on ROS, but not in communications, but my understanding is that the transport layer is totally isolated by using this data distribution service standard. So you can plug in any networking that supports this standard. And besides that, you can implement the RMW, ROS middleware layer, for example, with one of those protocols I showed you. So in this sense, it helps because, for example, the data distribution service doesn't require a master, so it's better for distributed systems. If your networking can make discovery with multi-hop, it will save you those issues, for example.
So perhaps you will recommend to, because my question comes from, I'm curious about when does it arrive the point where it's worth the transition from ROS 1 to ROS 2?
I think this is the question in all of our minds.
All of us.
I would say if you are starting afresh, go to ROS 2. If you have a lot of legacy code, you will have to check what of the packages have been already ported. There is a lot of work being done in porting packages, and for example, the last ROS 2 version was considered already long-time support. So
just double checking, when you mean legacy code, you mean my own code or seeing the packages that you
both things. I mean, if you have a lot of code that makes ROS 1 specific assumptions and you know for sure that some stack has not been ported to ROS 2, there is a bridge, you can try to play with that. But personally, if I'm starting something new, I would try ROS 2 to see how things go. If I'm supporting some old code, I would stay for now.
Okay,
but that's personal impression, of course.
Your research internals was like impressive. Thank
Sorry?
you.
I'm going up. I cannot hear well.
Your research was impressive. So I had like few doubts. Like when you're showing the video, like what's the FPS? How many frames were you sending from the robot, and how many were you receiving? Because you said like 300 milliseconds delay.
Actually, I don't know that part, but I guess as long as there was no interruption, mostly all the frames were arriving. We are talking about the first experiment with teleoperation.
Yeah, I mean, in that tunnels we are showing the video. Even in the when you're showing the RTWMP protocol, you're showing the video. Second thing is, which layer does it use? Like, in what OSI layers do you use your?
Actually, the protocol has evolved over time. At some points, it has used directly UDP. Other times, it has used row sockets directly. So.
I can hear you. So.
No, I'm saying that the protocol has evolved. I'm not the guy that has done the protocol. You can contact him for the truth. But I think that at some point it has used UDP. At some point it has used row sockets. I think right now, for example, you can use it directly with rows and rows with a wrapper. No, it replaced TCP.
Okay.
So rows it has a rows package that will get the topics and replicate them remotely, and the transport is the RTWMP. And also it can expose a regular Linux networking interface, so you can have SSH or whatever, regular communications encapsulated in the protocol.
So it's kind of like an application layer, you have one thing and...
Yeah, it's kind of a transversal thing. It depends on what you need.
I mean, when you're showing the protocol, you have like a fixed nodes and a robot going through the nodes, right? So which means it has infrastructure. So when you showed the first set of slides, you had like a fixed wireless nodes at a couple of points, and a robot is going through the transiting through the map. So which means it's like infrastructure model rather than a mesh, right?
No. It's not infrastructure. Those nodes were static, but they could be moving robots also.
Yeah, in the tunnels you are showing moving. Right?
Yeah, yes. And all the nodes are equal. There is no special nodes that are stations or...
So do we need any Wi-Fi? I mean, do you have like a code which is online, and do we need a special hardware like a Wi-Fi?
No. I think there are many cars that support giving you the quality, either directly or with minor driver modification in Linux. And for sure, my colleague has the code online, so you can check online, contact him if you don't find something.
One last question, I won't bother you. How much bandwidth were you like transmitting from each robot, like roughly? Like how much do you think is good?
I don't know. I'm sorry. In my own experiments using the network, I was using like 10th of kilobytes, so I was not stressing the network very much. But I don't know. Sorry.
I have one more question. So because we use drones and you have like antenna going in azimuth and elevation both, do you think we should require like a different antenna design that can help for drones?
Well, for hardware questions, I'm afraid I'm not the best person to answer. But they say that the higher the antenna, the bigger the antenna, the better. That's all I know. Okay.
First, regarding your first part of the talk, have you seen any difference when you put your Wi-Fi modules on the drones, or compared to when you keep in your hand and moving around? For example, I don't know the effect of the motors, propellers, body, in throughput.
In truth, I have not done, me personally, experiments with drones yet.
I mean, not drone with any robots.
Across different ground robots, there is a difference. If the antenna, because the robots are not perfectly similar, so they are mounted slightly offset or things like that. Some of them have different components, and we are seeing differences because of that. In drones, I fear that when you are communicating with the ground, if you only have one antenna upwards, maybe if you have one upwards and another downwards is better.
Okay.
For example.
And my second question is about how you can optimize the number of hops in your algorithms. For example, because I saw that you fixed the number of hops in some of your results. You know, for example, when you increase the number of hops, also the delay also increases. But for example, sometimes having 2 hops with a not really good link quality between the hops is better than having 3 hops with perfect link quality.
Yeah.
So,
in this sense, there are ways of detecting how well connected your network is. If you have a lot of links that will break your network, or you can have 2-node redundancy and so on. In this sense, Tony Franchi has a very interesting paper where they use the Laplacian of the connectivity matrix to ensure that connectivity is preserved and you can get more connectivity. Maybe that can go in the direction that you are asking.
no, because
I'm not sure.
No, it's not a matter of connectivity. I'm saying that if you increase the number of hops, for sure you have a better connectivity, but your throughput decreases.
Ah, yeah.
Yeah, I'm saying how you can optimize the number of hops.
Well, if you have a quality map of the environment, you can try to optimize the hops by using that information. Just
So
like
it's kind of exhaustive you are saying, because it's not also the matter of quality. As I said, for example, with 3 hops, your link quality is perfect, but with 2 hops, your link quality is not good, but the throughput is good.
I'm not sure I'm understanding 100%, but
So
maybe
because
it's
the drawbacks of usually the mesh networks and the routing algorithms is that, so for example, they try to, the final goal is to try to maximize the throughput, right? Because you wanted to transfer something.
Okay.
But sometimes actually the drawback and the bottleneck is this, according to my experience, sometimes by having 2 hops, when the quality of the link between the hops is not good, your throughput is better than by having 3 hops.
Okay, yeah, that I will put that into the capriciousness of the network. So, well, now that you have that experience, maybe that's something that can be researched further. Of course, the quality is only an indirect indicator. And as I said, it only is measured over part of the transmission. So if your real metric is throughput, maybe you need to optimize based on measured throughput instead of measured quality. Or maybe you have to use the quality as a worst case and the throughput as the guiding metric. It's an idea.
Do we have another question from the audience? Yeah. Yes?
Just like a general one. So if you have to suggest the audience one specific important topic of research to work on, which is the crossroad between multi-robot systems and telecom communications, what would you suggest to work? What is really unsolved or still very challenging, or but at the same time general, okay? Not.
Well, I think that I'm particularly interested into, when deploying the team, gathering the measurement of the quality and using that measurements to plan the deployment, the optimal positions. And so to me, the topic of enforcing connectivity in multi-robot missions is still open, and if you are able to do real experiments, to me that's the most interesting part. So I would say, yeah, basically what the DARPA challenge is, is going to do. So to work in real complex environments and try to see what happens.
By the way, as a follow-up, since for you, it would be reasonable to have multiple phases, like first use your robots to create a model, to learn a model about link qualities, about all this, the multipath, fading, all the things. Okay, I've been doing that kind of things, precisely. So instead of using the most obvious models that are beautiful but terrible, those mathematical things and approximations, rather than using machine learning in order to learn model, trying to somehow, to deploy the robots in strategic things and try to learn a mapping that then can be used for planning and then maybe adjust it. So what do you think about this?
That's something I have not seen, so probably it's a good idea. I wonder if a two-phase actuation may be too time-consuming. Maybe since in exploration you are going back and forth a lot because you are chasing frontiers, maybe in that case you can leverage the information you are gathering at the same time, instead of doing first a total reconnaissance and then doing the... But for sure what you should suggest sounds very, very interesting.
So I have also one even maybe more general question, also connected to like swarm robotics or multi-robot systems. Like today, one of the strongest motivation for using swarms is the lack of communication in large groups of robots. And we have really experienced in the field that it's difficult to connect more than 5 drones together if they are flying somewhere not in really open space. But there is maybe coming some like 5G networks, and these promising technologies, they promise like to have connected everything on the planet, like even your pen, and with extremely fast connection and whatever. What do you think? Does it have still sense to consider this limitation in our research, or we should just wait?
Well, for certain, there is here important technological aspect more than scientific aspect. That, of course, better technology will simplify these problems. But about 5G, I don't know a lot, but the few things I have heard is that it will work very well at very close range. So you basically, for localization, for example, I see your face. I'm not an expert here, so if you want to, but that's what I heard, that if you have lots of transmitters, you can get very precise localization, for example, very good throughput, but I don't know. Really, I don't know about 5G.
Okay, thank you. So yeah, thank you again for your first presentation. So afternoon we will have the second one from the other group. So thank you for providing me this option to give your talk twice. Thank you very much for that. Yes. So. Do we want to tell something today, right now, or everything can be said later? Yeah. So the only information regarding the certificates and the other documents I have signed already. Everything what was prepared there. So if you need these papers, just take it there. It's in the registration desk. Yes, thank you for the important information. Beer is already ready for you. So we have prepared some glasses with beer to fasten the lunch, because we would like to start sooner. So for you, once you are ready with lunch, please go to the rooms. No. After lunch, there is a presentation of Gengen. So sorry. So we will start here after lunch. What time is it now? So in 35 minutes, it should be enough to take some food, take beer, and come back. Thank you.